All right, we are starting a little bit late because I screwed up again on this video. Students are currently discussing a slide that's not up here. We did this, hold on. We did this bell ringer if you want to look at that. We did talk about the difference on this slide between laws and models. We can talk about that later if you want. But now they're discussing if I throw a bowling ball to the back of somebody's head in space, are they okay? All right, here we go. I'm not looking for a vote here. I just want a few pieces of anecdotal data, meaning I want a couple people to answer out. What do you got? Is he okay? No. No. Okay, why not? All right. So wait, but I think that some people will counter you here. So who is going to disagree with Isaiah that he's fine? Tessa, go.
Okay,
Don't worry about being right or wrong. You're going off of this is what I think and why.
The other day you discussed how like in space our weight would be like a small amount compared to what it is now.
Correct.
So like compared to the bowling ball, it'd be like a lot less, and then nothing. You throw it at him and like he'd be fine.
Okay, so the idea is, if I'm summarizing correctly, you believe Aiden will be okay because it's not as heavy.
Yeah.
Okay. Is that everybody who kind of feels that way? Is anybody want to add to that statement before we move on? You're adding or you're countering?
Kind of adding, kind of adding.
Sure. Rihanna,
Okay.
let's kind of add.
Okay, so I think that Aiden's gonna be okay, and when the bowling ball hits Aiden, the bowling ball is gonna stop, and then Aiden's gonna keep going. Aiden's gonna go.
Okay, but he's okay.
He's gonna go fly.
So do you think he's okay because of the same reason? Okay.
Pretty. Yeah.
Isaiah, sorry, no, go ahead.
I think he's gonna not be okay.
Let's make sure we're respecting people that are talking here. You think he's not going to be okay?
Even if both of them are lighter, like it's still the same percentage of his weight. Like they're both lighter. It's not like he's the
Interesting.
same. It's a lot less.
I've never heard that line of logic before. That's interesting. Okay. Yeah, Aiden. Is Aiden going to be okay, Aiden?
I'm not going to be.
You're not going to be okay. What's your line of logic?
Don't they simulate gravity on the space station? So it would be the same, like, force.
What do you mean simulate gravity? Do you think we have artificial gravity on the space station?
Well, I mean, no, but like, it's.
I need
it's
you to
not
watch
like
a
being in
YouTube
space.
video of the ISS. There's a stupid amount of them. They float.
Well, yeah, but it's not like. It's kind of like it goes back to the ratio thing, but it's not like they float as high as they do like they would on the moon or something.
They don't float on the moon at all.
Well, no, but I'm saying like.
There's gravity on the moon.
Well,
Correct.
yeah, obviously, but I'm saying like when you jump like super high on the moon, right, or something
Sure.
like that.
Less
You know?
gravity. Yeah. But on the International Space Station, you jump and you hit the ceiling.
Right.
I don't think this is going how you think it's going.
No,
All right, we're going to leave it at that right now because you guys have your personal views on this, and that's all I really wanted to establish right now. I'm going to answer this question, but I'm not going to answer it right now. What we're going to do right now is we're going to play a rousing game of Sally Ball. Sorry, people on the video. All right, so to play Sally Ball, I need everybody to the back of the room, and I'll bring Sally. Here we go.
Anyway, birthday.
I love that you guys are so worried about that.
I'm not. Please do not slow down.
All right. She's pressed on the line. Apparently, this is where we line up. You can be anywhere back here. Let me explain the game before all of you stand there, because I would suggest none of you stand there. All right. So I need 2 volunteers before I explain the game. Yes and yes. All right. So we'll have other volunteers throughout. Here's the game. It's a race. Okay. You guys are going to be on a team, and you're going to use your Sally thwack and stick. Okay. And you're going to whack Sally. Okay. And the idea is you're going to push the bowling ball around these 4 chairs. So don't be around these 4 chairs. Okay. Anywhere. Go over here. Sit. I don't care. Sit on the table for all I care. Not on the ends though. They're not well supported. All right. So you're on a team. You're working together, kind of like a hockey thing, but it's a race. So the idea is, I need 2 timers. All right, good to know. All right, and the idea is you want to get around these 4 stools as quickly as you possibly can. Yep.
Are we like just going in a circle, or are we supposed to like loop and just?
Nope, you just go all the way circle. That's it. Okay. And you're gonna go. You're gonna leave this square, and all you have to do is return to the square. You don't have to stop. You can roll right through. But if you roll through this square, we don't stop. You just keep going until you go through that square right there. Okay. Now, here's the big caveat. The big caveat is we're gonna time it, but also we're gonna add 1 second to your time every time you hit Sally. What? So. It's just the game. What do you like I'm indignant here. Like, I've made a rule that's unfair to the game that you just found that existed 30 seconds ago. Alright, so that's the rule. So you try to hit it as few, obviously you have to hit it, but obviously you want to hit it as few times. Does it make it worse when I make a pronoun in there? Alright, with the bowling ball, you hit the bowling ball as few times as possible while trying to get it around as quickly as possible. I will count penalties. A couple others, rule caveats, because someone's tried this before. I'm just going to hold it on there the whole time. I will count penalties as fast as possible. That does not count as one touch. 2, if you hit other people or other things, I'm going to decide a penalty on the spot that's going to be more than 1 second. Okay? So I'll count penalty. We'll add it to your time at the end. We'll see how you score. We'll see how somebody else does. Yes?
Okay, I have 2 questions.
2 questions. I have 2 answers.
Do we have to like stay together, or like can she go over here?
Do whatever the heck you want. It's like move around like hockey. Yeah, you're fine. Okay. And 2.
Like how you said like.
Yes, cruise control is a thing. Sorry, that's not it.
If it doesn't go this way, it goes over here. Do we have to go all the way around again?
No, you just go to that square as quickly as you can. All right. Our first time, first hit doesn't count. Who started?
Me.
Good. All right.
I'm adding in that corner.
Timers.
Around you and you'll be.
Timers, are you ready?
Yes.
All right. On your marks, get set, go.
Wait. Oh wow, that's heavy. Okay.
1.
Oh my God.
2.
Go get it. Go get it.
3. 4. 5, 6.
Go get it.
7.
It won't go.
8, 9, 10. 11, 12, 13.
I'm so confused what's happening.
14, 15, 16, 17, 18, 19, 20. Don't hit yourself. 21, stop left. 22, 23, 24, right here. 25, 26, holy crap. 27, 28, 29, 30, 31. You missed it again.
Oh no.
32, 33, 34, 35, 36, 37. Done. 38 in. 40 seconds. So, about what you got? Yeah. Okay, 78 is your score. 40 seconds plus the 38 hits or penalties or whatever. I need 2 more volunteers. Okay, yes and yes. Pop one up. All right.
3 seconds.
All right.
Seems difficult though.
Okay, on your marks, timer's ready.
Yes.
On your marks. Get set, go. 1, 2,
You idiot.
3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, done! What'd you get? 25, 19, 44. Not too bad, not too bad. All right, would you like to see me show off in this game that you just found out existed a minute ago?
Yes.
This feels like a weird flex. All right.
Go.
Aaron Preston, would you count my penalties, please? Remember, the first one doesn't count. Timers, are you ready?
Yeah.
Count me down, let me know.
3, 2, 1, go.
Oh, see, that's, yeah.
12, 18, not bad. All right, again, it's a weird flex, though. Look at me showing off in the game. You just realized. See, I'm not great at sports, so if I make up a sport and I can destroy people at it before they know the correct logic, then I can feel good about myself. Let's go sit. All right.
Ow, my feet.
Why don't you do?
This is what we should do the last day of school. We should just play
Love
seven
Sally ball every time. You're just hitting the bowling ball in a circle. That's all it is.
So I don't have bowling ball, so it's like, that was a lot harder.
I feel like Sally ball needs to be a sport.
All right. Handful of questions before we move on, given Sally ball. Number 1. Was getting Sally going fast a good idea? No? Yes? Why not?
But the faster you go, the faster time happens. but if you suck at hitting it like us,
Mixed
it
balance.
doesn't go very well.
Fair enough. All right, number 2. Hitting Sally does 3 things. What are they and why? And by the way, depending on how you answer this, you could answer technically 2 or technically 1, but let's just say it's 3. And discuss quickly in your group, real quickly, what are the 3 things that Hitting Sally does? I'm only going to take like 20, 30 seconds on this. Go quick. Hitting Sally, what does it do?
For a better man. That's actually.
People online, I guess discuss with yourself. All right, what you got? What happens? What do we do? What does it do? Hitting Sally does 3 things. What's one?
The acceleration of Sally.
I'm gonna say, if you say acceleration, then technically I'm going to go ahead and say that's the one thing that you can say. So let's break that down a little bit further. You're right. 100% you're not wrong. Yes.
Change direction.
Change direction is 1. Yes. Change direction. What else? And again, if you do it like that, then it was technically 2. So that's 100% right. But what I was looking for, yeah, go ahead.
Does it change its velocity?
So let's get to all of that together. Here's what I was looking for, and let's put that in a nutshell. I was going to say change direction, speeds up, slows down. Now, if you didn't get this, you're not wrong at all. You shouldn't have necessarily got here. Literally saying acceleration means you're good. That's what Hitting Sally does. Because what I wanted to cover real quick is this. If you'll remember, what's the definition of acceleration? Correct. Changing velocity. Now, what you have to remember is that velocity is speed, since it's a vector, plus direction. So basically, to change velocity is changing either of these 2 things. So the last 2 things here, of course, how you change speed and then change direction. Now, you guys are mostly used to these 2 things on any type of an assignment whatsoever. We a little bit dealt with the second one, but not directly. But what this actually says is that it is possible to not change speed at all and still accelerate. Okay, what do? How would you change speed, not change speed, but still accelerate? Change direction. And if you don't believe that's true, try to get off the interstate going about 100 miles an hour. Okay? Or going too fast. Don't do that, by the way. I don't actually want you to be like, well, Spainhour said, here we go, planning this one out. No, don't do that. But if you ever try to get off too fast, you can feel the necessary acceleration to change direction. We'll talk more about that in chapter 7. Point of this is Hitting Sally does the 3 things: speeds up, slows down, changes direction. Last question. Would playing Sally ball be easier or harder if you played with the tennis ball? Discuss in your group. I would find it hilarious because you'll have 2 people separately in the room. One who goes, oh, and then like it's obvious, like, it's easier. And someone else goes, it's harder. Like it's the most obvious thing ever. By tennis ball, I don't mean kickball. By tennis ball, I mean tennis ball.
It would be harder because it's harder to hit. Because the stick is small and the ball is small, and I have bad hand-eye coordination, so it would be
Let's go ahead and assume the same athlete in both cases, so the same object.
Same athlete would be easier to hit. It'd still be easier to hit the bowling ball with the stick.
Well, let's agree to let's see what everybody else says. So you say it's easier or harder with a tennis ball.
I think it's easier with the bowling ball.
Why would you take my question and do the reverse? That hurts a little bit. So it's harder with the tennis ball is what you're saying. Okay, anybody disagree with that? Okay, why do you disagree?
Because the tennis ball is easier to push and change the direction.
Fair enough. Okay. We're not going to. We don't have that kind of time. We do have stuff we're doing today. Believe it or not. Yes.
I think if you hit, when you hit the bowling ball, you have to hit it kind of hard for it to change.
Okay.
If you hit the tennis ball hard, it's literally gonna just leave.
So what's interesting about your guys' 2 arguments just there is you said the opposite, but for the same reason. Okay. You said it's easier because it's easier to change its direction. You said it's harder because it's easier to change its direction, right? Just the idea being, if you're not in control, it's going to go crazy fast. But also, if it's going crazy fast, which one's going to be easier or harder to stop? tennis ball is going to definitely, we all agree with that, right? So we agree with the tennis ball would be easier to get going and easier to stop. Now, let's address this. The bowling ball and the tennis ball have two major differences. What are they? Mass. Why are they different masses?
The bowling ball has more atoms.
Correct. And what's the second major difference?
Volume.
Okay, agreed. I'm sorry, I wasn't looking for that. But you're 100% right on that. That's not the one I'm looking for. So, okay, three differences. Let's knock that one out. What else is there?
Size.
It's not quite what I'm looking for. That's volume. Yeah, the force of gravity, or what most people call weight. Now, but we've already discussed that weight and mass are intricately related, right? It's why most people screw this up. Yes, this has more mass because it has more atoms, but it also has more weight because it has more atoms. But the nice thing that you have right now is that you exist in a time when space travel is a thing, because it's kind of cool, because if I took these two objects and I took them up to the International Space Station, would they have the same mass as they do now?
Yes.
Yes. Would they have the same weight as they do now?
No.
No. What would their weight be up there?
Significant.
So they would have the same weight up there. 0. Yes? So, with the International Space Station, we can really get a feel for the difference between these two. But real quick, I realized that I kind of forgot this real quick. If you haven't got that down, make sure that you say something about this in your notes. Okay, I'm not going to spend a lot of time on the slide for you to write it down, but this is online. So yeah, the three things that hitting accelerate does: speed up, slow down, change direction. But JK, all of those are really just acceleration, because all of those are different examples of changing velocity. Again, I'm not leaving this up here, so if you want it, check your notes online. They're already up there. Actually, they're not. I need to do that before the next hour. Okay, mass or weight? Do objects in here have weight? We already discussed yes. The bowling ball has more weight. Do they have mass? Yes, they both have atoms. What's the difference? We already discussed that. What about on the ISS? We already discussed that, so let's move on. Here's the nice thing about if we watch a video on the ISS. Now, here, that one has more weight and it has more mass. But on the International Space Station, this one has more mass, but they have the exact same weight. Yes? So we can really sense a difference up there.
I mentioned earlier, one of the properties of mass is that bodies with greater mass are accelerated less by the same force. We're going to use a force as provided by a tape measure. There's a spring inside a tape measure, and we will use that as a force to act on an empty bag of water, a full bag of water, and then we have a surprise guest that will try to accelerate as well.
That's hard to do on the ISS. Usually you want to schedule those things. It's not easy to just stop on. So before they do this, again, just want to remind you, full bag of water, empty bag of water. Which one has more mass? Full bag. Full bag, okay? But they have the exact same weight. So what we're seeing here is if it's weight that affects an object keeping going, then it should have the exact same impact up here, right? You pull on the heavy thing, you pull on the light thing on Earth, it should have the same impact because they have the exact same weight. But if it's mass that affects it, well, masses are different, and so it still should be different on the ISS, even though there's not force of gravity anymore. Here, I think this is the empty one.
And Koichi now will release the spring on the tape measure. Let's see what happens to an empty bag of water. It accelerates very quickly. So we see that a body with a very low mass accelerates very rapidly. Let's do the same thing now with a full bag of water.
So predictions. It'll act exactly the same or it'll be different. What do you got?
We'll stretch the tape measure out to 1 meter. We're out of the field of view. Let's bring it around here. And now, okay, now we're in the field of view. And now we're ready to test the mass.
Was it the same? So what impacts how hard it gets accelerated? Mass.
So a full drink bag accelerates, but at a lower rate than an empty bag. Let's try one more object, a little bit heavier, a lot heavier than a drink bag of water. I'm going to ask Koichi to see if I can accelerate. So I'll be on one end of the tape measure, and we'll see if the spring will accelerate me.
By the way, if you were kind of curious why they're standing upright like that, it's because they are literally locking their feet into the ground right now so that they can be upright in the video, because it would be weird for you if they were just floating all over the place.
So I'm holding on to the end of the tape measure.
So now he's
Lift my feet up off the floor. I'm now free floating inside the Japanese
letting
lab.
go his feet off the floor now. So now you can see what's actually.
And very slowly, the tape measure spring is pulling me towards Koichi. Much, much slower than the drink bag. Even large masses can be accelerated. So
a couple things to point out here. Number one, kind of not physics related. ISS is a really cool thing. If you ever get a chance, watch some videos on it, like take tours around it, because it's kind of fascinating how they position everything, and just there's this weird stuff with the way you sleep kind of messes with your perspective of what's down, and there's a whole conversation there. But another really cool thing about it is the ISS, International Space Station, is made up of different, nations. And so there's this weird political thing where technically they have to cross borders, like where there's actually like borders on the ISS, but there's like treaties basically written that you can freely cross borders on the ISS. So that being said, we are currently in Japan on this particular video, and of course the gentleman with the patch on the side, hopefully you notice, is not American. But a couple other things to point out, more physics related. So, does he accelerate?
Slowly.
Yeah, why does he accelerate slowly? Because he's got more mass. That's it. So, we come down here, and just to prove that he's actually accelerating, I do want to show you this real quick. Going back to the
now
video,
free floating inside the Japanese
shoot
lab.
ahead, just so you can see, okay, he's going slow. When they scoot ahead a
Much,
little bit,
much slower than
he's
a
going
drink bag.
much faster later on, yes?
And very slow.
Oh, sorry, that's
But
too obvious.
inside the Japanese lab, very slowly.
And then much quicker at the very end. Sorry, not much quicker, but quicker. Definitely he has a higher velocity. That is to point out that it's not just moving slow, but it is in fact accelerating. All right, now, what do we do with this? Well, we're starting to answer some questions. Why is the bowling ball hard to get going?
Yeah, more math.
It has more atoms, not because it's heavy, but because it has more atoms. And that kind of makes sense, because here's what Newton's first law is. If I roll a bowling ball, you're not gonna write this down yet. If I throw a bowling ball in space, what's it gonna do? Forever. Constant what? Velocity, because it's not gonna change direction and it's not gonna change speed. Now, if you were to roll a bowling ball here on Earth in a very long hallway, so a long enough hallway that we wouldn't expect it to run into the wall, would it eventually stop? Yes. So that leads a lot of people to naturally think that objects naturally stop. But what's the difference between the two, the bowling ball thrown in space versus the hallway?
Wait.
Gravity. It's not the major difference. You're not wrong, but also friction. The bowling ball is running into air, and it's running into the ground, just holding on to it. So there's another force present. But if there are no forces present, what do we naturally expect an object to do? Keep going. Now, if I throw the tennis ball and the bowling ball at the same velocity, same thing, right? You expect them to go at the exact same velocity. That is Newton's first law. What do we expect objects to do? All objects will stay going at the same velocity. Definitely write this down. Unless there are no forces, space, or balanced forces, which we'll talk a lot more about next week. So all objects, the tennis ball and the bowling ball, want to both go the same velocity. But one of them wants to go the same velocity sort of more. Which one wants to go the same velocity more? Try again. The bowling ball. Because it has more mass, aka it has a property known as inertia. Inertia is the name we give to this idea that all mass wants to go the same velocity. Or you could argue it's the ability or how good an object is at staying that same velocity. And that's measured by mass. Yes, Chloe?
So you said that everything in space has no weight because there is no gravity.
Because there's no second object, yes.
So like
no weight.
There's a few tricks to what we're talking about here. Like, we'll come back and talk about the ISS on that no gravity situation. But if you were out in the dead of space, yeah, no gravity up there, so it would just stay going forever. Now, hey, I said this is measured by mass. So which of these two objects has more inertia then? The bowling ball, because it has more mass. And that means we just developed a second property of mass. The first one, if you'll remember, is gravity. We talked about it on Monday when we said there's two properties of mass. You're going to have to go back to those notes to fill in the second one. The second property of mass is inertia. So I will ask you throughout the year to tell me what the two properties, don't write down, listen for a second, just for a second. I will ask you throughout the year, what are the two properties of mass? And what I'm looking for as an answer is you'll say, all mass attracts all other mass, and all mass wants to stay going the same velocity. Now, the names for those phenomena are gravity and inertia, respectively. But the actual what it is what I'm looking for. Those are the properties. This chair is attracted to that tennis ball. That's gravity. If I throw the chair at you, the fact that it wants to keep going is inertia. Now, this is, by the way, I'm going to take off this slide, but this same thing will hang around. So if you're just kind of, while I talk about a few examples. So let's say you've got two cars. These two cars in this picture. You've got to help both people in these pictures, or you get to choose which one is going to be easier to get going. Correct, because less mass. Which one's going to be easier to stop? Because so mass has effect on both changes in velocity, both speeding up and slowing down. This one's harder to get going, but it's also harder to stop. Let's say you're taking groceries in from outside and you've got a bag full of paper goods and you run into the wall. Is it usually that big of a deal if you accidentally run into the wall with a thing of, like, paper plates and plastic forks? Is your hand okay? Yes, but imagine you go back to the car and you get a thing of canned goods and you accidentally run into the wall at the exact same velocity. Is it okay? Not as much. It's going to hurt a lot more. How come? There it is. Going to your next class, you see standing in front of you a linebacker from Ohio State and Spainhour. Both of them are going to run at you, and for whatever reason, hypothetically, you have to stand in front of one of them. Who are you going to choose?
You.
Why?
Because you're not.
Because I am going to be easier to stop, because now there's no fancy thing, it's not muscles or anything. If I strapped on weight to my back to have the exact same mass as the linebacker and we ran at you at the same speed, then it would be the exact same effect. That's all it is. Here's another couple of examples. Let's say we want to hit Spainhour with a hammer. Let's say that.
Hey guys, so I talked to you about an example about me getting hit with a hammer. So here we are. The question comes down to it is, I'm going to protect myself from either.
Yeah, but it doesn't do what we need it to do because you're going to want to see it.
Hey guys, so I talked to you about an example about me getting. Hey guys, so I talked to you about an example about me getting hit with a hammer.
Sorry, we'll fix it. It works for a shower just fine. Yep, there is.
Hey guys, so I talked to you about an example about me getting hit with a hammer. So here we are. The question comes down to it is, I'm going to protect myself from either a 50-pound weight. Okay, either that's a 50-pound weight, or I'm really good acting on camera. My regular hammer here.
I'm going to finish these notes on the recording after you guys leave and post it. There's going to be about 2 or 3 minutes more to this. So if you want to check it out later, great. It's going to kind of be helpful. This way you can get to your next class and still check it out. But I'm going to pause over here. All right, let's finish up the notes here. Everybody left.
Or with a 50-pound weight protect me, or what if I just use a washer? Will that protect me? So, got a lovely assistant here, and then if I die, we have video of it. So, here you are, sir.
I hope I don't die.
I missed. Let's try that. Here we are. Here we go. All right. Ready? Give her a swing, don't miss. Seems pretty solid. Let's give her a bigger swing. Let's see what we got. And feels pretty good. All right. Let's check for sake of seem to be sadly the same size. Seem to be. All right. So now let's go ahead and got the hammer there, and let's go ahead and try with the washer. That would be the beginning of I believe it's the word is manslaughter. We're not going to do that. So all right, that's it. Hey guys.
Question in play here is why does the giant mass protect me? And the answer is, as we've discussed, it has a lot of mass and therefore it is hard to accelerate. So the hammer hits the 50-pound weight. The 50-pound weight hits me, but it's not going very quick because of this. This was used, this is sort of the idea, one of the ideas behind, excuse me while I try to do three things at once. This is the same idea as like medieval armor. When you swung a sword at somebody, people think about it's protecting against like the slashing or the piercing, which is true, certainly, but also just having more mass on an individual meant that you weren't going to hit them as hard with the sword as obviously somebody who didn't have armor. In addition, it also added the benefit that you weren't going to move a knight very quickly around a battlefield like if you were shoving them or whatever because they were heavy enough. But let's look at one last example, one final slide, and we'll be done. All right, so there's Spainauer getting hit with a hammer. We did that video. What about this? You ever tried the dishes on the tablecloth trick? You put a bunch of dishes on the tablecloth, you yank that tablecloth, and they don't move. Think about which one would be easier. Actual plates, like actual china on your table, and then you yank it, or whether or not you try to use like paper plates and plastic silverware and plastic cups. Which would be easier to pull this off with? Well, let's see a demonstration here real quick. No, show the video. Are you kidding me? This worked in first hour.
Hi, ich bin's Michel und ich bin Sven und wir zeigen euch heute einen
German.
ultimativen Trick.
Yes, it matters. So watch carefully the plates. The plates don't move. That did. So let's analyze this video again from a non-physics standpoint because it matters to me. Number one, the small kid. Why does he stand behind the big kid? Like, it's like they're trying to make a video. But also, that kid's dead, all right? If you look at that video, that TV, that is a CRT. That's not a flat screen TV. That child is very likely not okay. They were trying to make a viral video, but like, yeah, that kid's not good. Also, I don't know why this matters, but I show it every year. I think I'd be decent at dubstep. Like, watch this. Like, just watch this go away. Oh, faster. Hi, I'm Victor Sven. Anyway, not important, but it's kind of important to me. All right, last thing to go over here real quick. Oh, let me answer the earlier question. The earlier question of what would be easier to pull off. It should be real plates as opposed to plastic plates because they are more massive. And this final slide here, this is a quick review overall of Newton's first law. Okay, this is how I personally like to see it. Like, how do I know something's following Newton's first law? Look at this first bullet point back here. I don't know why I went so fast. It's going at a constant velocity. If you see a person walking across the front of the room at a constant velocity, or a car traveling down the road at a constant velocity, you know it's following Newton's first law. What does that also say? Well, constant velocity, just basic kinematics, tells us that that acceleration is zero. It's not changing its velocity over time. But also, as we said in the thing, we also know that forces, either there's no forces or they are balanced. Balanced forces, yeah, well, that's like what we did the other day on the force diagram. This is the car traveling down the road at cruise control. you'll notice that force normal balances force gravity, and force engine on car balances force friction. And where am I going to have to go for no forces? Space. This is Sally floating in space, and unfortunately, oh, she's so alone. That's depressing. Anyway, you're going to have to go to space to get no forces. That is the force diagram, by the way, correct one on Sally. There are no forces on her. And if you look to the left here at the car, if you're here on Earth, yeah, there's definitely going to be gravity. There's more than likely going to be friction. So we are regularly going to be dealing with balanced forces. And that's Newton's first law.